Hello, and welcome back to a video series on MAC 1105 College Algebra. My name's Sean Perry. These are guided notes number 15 in the series on section 3.7, distance, midpoint, and circles. Many of the formula that we're going to use today are derived from the Pythagorean theorem, so it would be helpful to at least look at a sort of proof, a picture proof, about why that theorem is true. Consider these two squares, A and B. Notice that both of them have sides little a plus little b. And so they both must have the same area, which is little a plus little b squared. Notice also that we have two different ways of arranging some shapes on the inside of these two squares. Either I can make it so that there are these two rectangles and two little squares, or so that there are these four right triangles and this one bigger square. We can also get the area for A and B by adding up the areas of the smaller figures. The two rectangles both have area AB. The square of side A has area A squared. The square of side B has area B squared. And these shapes together compose square A. On the other hand, square B has four triangles, which each have area 1/2 A times B, and one big square in the middle whose area is C squared, where C is the diagonal of that right triangle. But now we just set these two areas equal to each other because they're both equal to A plus B squared. However, we notice that 2AB is the same thing as 4 times 1/2 AB. And so these terms would cancel from each side. And that just leaves us with the Pythagorean theorem. A squared plus B squared is equal to C squared, where A, B, and C are the sides of a right triangle, with C being what's called the hypotenuse of that triangle, or the longest side, the side which is opposite from the right angle. One of the first ways we're going to make use of this formula is by extending it to what's called the distance formula. This will give us the straight line distance connecting 2 points in the plane. Let's take 2 points, x1, y1, and x2, y2. We can calculate the distance between them by constructing the following triangle. Notice that the distance between x1 and x2 is the base of this triangle. Let's call that A. And y2 minus y1, this length here, is this height of this triangle. Let's call that B. And D is the hypotenuse of that right triangle. So from the Pythagorean theorem, we would have that D squared was equal to A squared plus B squared. And we could solve for D by taking the square root of both sides. This would give us D is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. So now let's apply that distance formula to a variety of problems. Say we were given 2 points. We should label them x1, y1 and x2, y2, although it doesn't matter really which one is called x1, y1 and which one is called x2, y2. If I gave you these 2 points in a different order, it would give us the same distance. And that's of course because if I reverse the order of subtraction here, but square it, I still get the same positive number. So plugging in these as they are to each one of these positions, we get the following expression. And we just want to evaluate and simplify that. 18 minus 3 gives me 15. 6 minus minus 2 gives me 8. Squaring each of these and taking their sum, I get 289, which is actually a square. It's 17 squared. And so taking its square root, we just get 17. Likewise, if I'm given a 0, it doesn't really matter. I just plug that 0 into the formula. x2 minus x1 squared plus y2 minus y1, and then squared. Keep track of the signs, right? When we subtract -2, that's adding 2, which will give me 8 squared is 64, 6 squared is 36. Summing those, we get 100, and 100 square rooted is 10. All right, let's keep going. Plugging these numbers in as such, we take our differences, keeping track of our signs. We square those differences and then sum those squares, which gives us this number, which I wouldn't have known, but for a calculator, has a square root of 101. Finally, we get one that doesn't completely simplify. Plugging in our numbers, taking our differences, taking our squares and our sums, we have a square root of 68 by the time we're done evaluating the arithmetic within the formula. 68 isn't a perfect square, but it does have a 4 as one of its factors, which is a perfect square who has a square root of 2. The other number is 17, which is prime, and so we just write square root of 68 as 2 square roots of 17. Here we're asked to find a distance based on a graph, but really all we need to do is determine what are the endpoints to A and B. So A is going to be the coordinate -2, -1. B is going to be the coordinate -1, +1. And plugging these into the distance formula, we wind up with -1 minus -2 squared plus 1 minus -1 squared. This gives me 1 squared plus 2 squared, which is 1 plus 4, which is 5. And the square root of 5 does not simplify, so we're going to just leave it at that. This line segment has the length radical 5. So now let's talk about the midpoint formula. The midpoint formula lets us find the halfway mark that is half the length down a line segment. If the line segment had length d, we're going to be interested in what value is half of d down the line segment this way, and therefore half of d down the line segment this way. We'll call this point M. And what we can do is construct similar triangles to see that this coordinate is also halfway between the coordinates x2 and x1 and halfway between the coordinates y2 and y1. Here are those similar triangles. Notice if this one has length 1/2 d, because all their angles are the same, this length here must be 1/2 y. And also this length here between these 2 points from x1 up to this middle x value here, this must be 1/2 the original distance between x1 and x2, because this little triangle here is similar to the big triangle, so they must have the same ratio of sides. Now, how do we find what's halfway between the x's and halfway between the y's? There are a few different ways, but here's an easy one. We just take their average. This will give us their middle point, and that tells me the coordinates of M. M will be at the coordinate x1 plus x2 over 2, y1 plus y2 over 2. Let's now practice using the midpoint formula. Given 2 points, all we need to do is take the average of the x's and the average of the y's to find their midpoint. So the average of -7 and -5 is -6, and the average of -1 and -9 is -5. So the midpoint of the segment connecting these two endpoints will be at -6, -5. Likewise for this one, we plug in our points and take our average and get -5 over 2 and 1/2. Nothing says that it need be a whole number at my midpoint, even if my coordinates of the endpoints of the line segment are whole numbers. Here I have 8 and -2 for my x values. Their average will give me a 3. Here I have -13 and 8 for my y values. Their average will give me a -5/2. We could even have fractions for our endpoints. Notice here we want to take the average of these two x's, which means summing them up and dividing by 2, which gives me 4/3. Here I take 0 plus 3/10, and then we take the average of that. Notice we're dividing by 2 here, which is the same as dividing by 2 over 1. We flip it and multiply, and that gives me 3 over 20. So now let's talk about the circle. We've talked about distance. Let's talk about equidistance. A circle is the set of all points that are equidistant, or of equal distance, from a given point. Now, this distance is given a special name. It's called the radius. And this given point is given a special name. It's called the center. So we could say that a circle is all of the points at radius distance from the center point. And we could write that in set notation this way. If r is the distance between any x and y and this hk point, then using the distance formula, we would have that r squared was equal to x minus h squared plus y minus k squared. Now we could simply take this expression and square both sides. This gives us an equation, x minus h squared plus y minus k squared is equal to r squared, which looks very similar to the Pythagorean theorem. This is called the standard form of a circle, and coordinate pairs x, y are solutions to this equation if plugging them into this equation makes the statement true. That is to say, it gives me a value on the left which is equal to the value on the right. Now, we should notice that we are subtly introducing a new species of equation to you because we're dealing with these y's squared. We can't really solve for y the same way that we used to, not in a way which would give us a function anyway. What we're dealing with now is, in general, a two-variable polynomial. We have powers, we have sums, we have coefficients, we have timesing by constants, but this is a very special form of a polynomial. Now, it's a second degree because the highest powers are 2. And really, if we just expanded out the standard form and collected like terms, we might get something that looks like this. A very standard question is going to be, how do I go from something which looks like this and get back to the standard form where I can see the center and radius of the circle very easily? So first, let's practice plugging things into the standard form. If I know my center is at -6, -12, and my radius is 2, I want to insert those for these 3 parameters. Here we know that h is equal to -6, k is equal to -12, and r is 2. Plugging those things in and collecting my signs appropriately here and squaring my 2, I get x plus 6 squared plus y plus 12 squared is equal to 4. It's no more difficult if they give us a 0. We want to plug that in for our k value here, which is just going to give us x squared. Minus minus 9 is, of course, plus 9, so we have x plus 9 squared here. And 24 squared is 276. So this is our equation in standard form for this particular circle. Finally, we have a square root. This is a pretty common thing to do for your radius, and the reason is because we're going to square that thing. And so when we square it, we get this whole number 6. Other than that, it's just plugging a 4 into these places. Notice the minus sign is here because it is part of the formula. This is x minus h, and here h is given as 4, y minus k, and here k is given as 13. Here they'd like us to digest what this circle graph is telling us. I've already marked it up a little bit, but we can note that it has a center at 0, 2 and a radius of 2. So how do I write it in standard form? All I'm going to do is plug those points into the standard form equation and simplify. What is the domain and range is an interesting question. We note this isn't a function, but it is a relation, and relations have a domain and range. What are the x values that got used? Well, you can see it's between -2 and +2. What are the y values that get used? Here I've shaded that in yellow, and that's from 0 up to 4. But there is a formula we could use to talk about the domain and range. We should notice that we can be at most r from the center. And one of the ways I can get r away from the center is by starting at the center and going to the right by r, which would give us this endpoint for the x values, or going to the left by r, which would give us this endpoint for the x values. Likewise, for my range, I could start at k, a y value, and go down by r or go up by r to get these points on the circle, which tell us our highest and lowest in terms of y. So our domain and range can always be found by adding and subtracting r to the h and k values respectively. Here we have another circle. It's got this center, this radius, and this domain and range. The center is at -3, -2, and its radius is only 1. We can get the standard form of the circle then by plugging those values in, and the domain and range are as follows. -4 to -2 for my domain, and -3 to -1 for my range. Notice that is indeed -3 plus and -1, and -2 plus and -1. This next one's already in standard form, so we really just need to decode that this has an h of -4 and a k of 0 and a radius of 4, because this is r squared. Graphing that would look like this. Here we have the center, and the radius is 4. Notice that if I go to the left by 4 and the right by 4, I could find its domain. And going up from the center by 4 and down by the center by 4, I get my highest and lowest y values, which would tell me its range. So these are our domain and range for this particular circle. Again, we can see that if it's in standard form already, it's actually pretty easy for us to decode the center and radius. So here we have -h, that means h is 5. We have -k, that means k is -7. And the square of this number here is 3, which gives us our radius. 5 minus 7 is down here, and going 3 in each way here, I could connect these dots to show me the circle. The domain is going to go between these 2 points, so that's from 2 up to 8, and our range is going to go between these 2 points. That's going to be from -10 up to -4. Let's look at another one that's already in standard form. Here, there's no term here that's being squared, no difference with x, so we can interpret that this is a 0. Likewise, this should be positive 7, and the square root of this would be 2. So we go to 0, 7, we go out 2 in each way, up, down, left, and right, and we complete those to make a circle. Here is the domain and range going up and down by 2 from 0, and going up and down by 2 from 7. Here we have the first question asking us to convert the general form of the circle to the standard form. As I mentioned, this is going to be an exercise in completing the square. The first thing I would do, though, is group my x terms together and my y terms together, because we're going to complete their squares separately. If I take a look at the x part, we want to take half of this and square it, and then add it into this slot here that I've left open. Make sure to do it on both sides. Likewise, with our 14 here, I take half of 14, which is 7, I square it, that's 49, and I add that to the other side as well. Now, 9 plus 49 is 58, minus 57 is positive 1. And so we complete the squares to give me x plus 3 squared plus y plus 7 squared, and that's equal to 1. Notice that this number here is going to be half of the value that was attached to the x here. And likewise, this 7 was half of 14. So we have a center at minus 3, minus 7. We have a radius of 1. And that gives us something we can graph pretty easily. Notice the domain, or the used x values, are negative 4 to negative 2, and the used y values are negative 6 to negative 8. The main idea here is I want to stress setup is everything. If we regroup things involving our x's, then leave a space, then regroup things involving our y's, and then leave a space, this will be a lot easier to do. I take 1/2 of this linear term's coefficient, negative 2, and that will give me a 1 when I square it. Technically, this should be a minus 2 and a minus 14, but remember, once I square it, that's going to make it into a positive number anyway, so these numbers that we've added here are still correct. We just want to do it on both sides. Now, this gives me a 9 on this side and allows me to complete the square here as x minus 1, that's 1/2 of minus 2, and y minus 7, which is 1/2 of 14. So now we know the circle's center is at 1, 7, and its radius is going to be 3. This is what makes it easy to plot this function and find its domain and range. Let's do that again. If I regroup this function, well, actually, I don't need to do too much, right? Because there's just this x squared term here. We don't need to complete that. We could just let this be on its own. We know that the x coordinate of the center is going to be at 0. And here, we want to take half of 6, square it, that's 9, add it to both sides. That gives me y plus 3 squared as the factored version of this polynomial, equal to 49. That tells me the radius of this circle is 7, and its center is at 0, minus 3. If we put a point at 0, minus 3, and we put a radius of 7 around that, we'd get this kind of circle, and that would give me a domain from minus 10 to 4, and a range of minus 7 to 7. All right, that's going to do it for this video. Thank you very much for your patience, and have a great day. Good luck with your studies. I'll see you in the next one.